Ever pondered what would happen if the fabric of space-time started behaving like a Möbius strip or a Klein bottle? Welcome to the fascinating realm of quantum field theory in non-orientable spaces. In the vast canvas of the universe, we often stumble upon ideas that challenge our understanding of reality. One such idea is that of non-orientable spaces, a concept that defies the traditional rules of geometry. Imagine a Möbius strip, a surface with only one side and one boundary component. Now imagine this concept applied to the entire universe. Sounds mind-boggling, doesn't it? Quantum field theory, or QFT, is the language we use to describe how particles like electrons and photons interact. In the usual contexts, we're working with nice, flat, and orientable spaces. But what happens when we throw non-orientability into the mix? This is the question that has been puzzling physicists for years. When we talk about non-orientable spaces, the rules of the game change. These spaces are bizarre, where you can take a journey only to find yourself flipped like a mirror image of your original self. It's like Alice stepping through the looking glass into Wonderland, only this Wonderland is governed by the laws of quantum field theory. The revelation is that quantum fields in these non-orientable spaces exhibit self-similar properties. This means that they behave in a way that is fractal, repeating their behavior at different scales. This fractal nature influences how fields interact with each other, leading to new, fascinating phenomena. It's like looking at the universe through a kaleidoscope. The same fundamental particles and fields are there, but the patterns and interactions they form are novel and intricate, revealing hidden aspects of quantum field theory that we're just beginning to grasp. To summarize, we've embarked on a journey through the looking glass, exploring the strange world of quantum field theory in non-orientable spaces. We've seen how these spaces, which behave like gigantic cosmic Möbius strips, challenge our understanding of quantum field theory. We've discovered that quantum fields exhibit self-similar fractal behavior in these spaces, leading to new and complex field interactions. And we've glimpsed the hidden aspects of quantum field theory that these spaces reveal. In the end, it's all about pushing the boundaries of our understanding, stepping into the unknown, and finding beauty and complexity in the most unexpected places, even if those places happen to be a universe-sized Möbius strip. So keep contemplating, keep questioning, and remember, in the realm of quantum physics, nothing is ever as simple as it seems.